Nothing is the most terrifying word in physics, not because it describes absence, because it might not exist at all. 13.8 billion years ago, everything that makes up the observable universe, every galaxy, every star, every atom of every planet, every photon of light that has ever traveled across space, emerged from a state so extreme, so incomprehensibly dense and hot, that the known laws of physics break down completely at the moment of its origin. The Big Bang is not a theory about something exploding into space. Space itself expanded. Time itself began. There was no container. There was no backdrop. The universe did not appear inside something else. It was the something else. Every direction you can point, every coordinate that has ever existed, every dimension in which anything has ever moved, all of it traces back to a single origin point roughly 13.8 billion years ago, when the temperature of the entire cosmos was 10 to the power of 32 degrees Celsius, 100 million trillion degrees, concentrated into a region smaller than a single proton. That is not a metaphor. That is a measurement. And yet, when you follow the math backward to the very edge of that moment, to what physicists call the Planck epoch, a window of time lasting only 10 to the negative 43 seconds after the Big Bang, the equations collapse. General relativity, the framework that describes gravity and the large-scale structure of spacetime, becomes incompatible with quantum mechanics, the framework that governs the behavior of particles at the smallest scales. The two pillars of modern physics, each independently verified to extraordinary precision, refuse to agree with each other at the one moment in cosmic history when we need both of them simultaneously. So the question is not merely philosophical, it is scientific, urgent, unresolved. What was before the Big Bang? The instinct is to answer, nothing. Pure, absolute, total nothing. The word sounds like an answer. It feels like a closed door. But the moment you ask a physicist what nothing actually means, the door swings open onto an abyss. Because in physics, nothing is not nothing. Quantum field theory, the most precisely tested framework in the history of science, accurate to 1 part in 10 billion, tells us something deeply unsettling about the nature of empty space. Even in a perfect vacuum, a region scrubbed of every atom, every photon, every particle, cooled to absolute zero and shielded from every form of radiation, space is not empty. It seethes, it fluctuates. At scales smaller than any particle we have ever measured, pairs of virtual particles continuously pop into existence and annihilate each other in intervals so brief they cannot be directly observed, only inferred through their measurable effects on the physical world. This is not speculation. It is observable. The Casimir effect, demonstrated in laboratories, measures a tiny but real force between two uncharged metal plates placed nanometers apart in a near-perfect vacuum. The plates are pushed together by the pressure of the quantum vacuum itself. The nothing between them pushes. Nothing has pressure. Nothing has energy. Nothing, in the language of quantum mechanics, is not an absence of reality. It is the ground state of quantum fields, the minimum energy configuration that the universe can achieve, and the minimum is not zero. Let that settle. The lowest possible energy state of the cosmos, the floor of physical reality, still contains energy, still fluctuates, still produces measurable forces. The most sophisticated vacuum that experimental physics can create is not nothingness. It is a churning ocean of quantum activity, invisible to every instrument except those sophisticated enough to catch the pressure it exerts on matter at atomic scales. This creates an immediate and devastating problem for the question at the heart of this video. If even our best modern understanding of empty space cannot produce true nothingness, if the quantum vacuum, by definition, is something, then the phrase, "before the Big Bang, there was nothing," may be not just philosophically unsatisfying, but physically meaningless. You cannot point to a state of absolute nothing and call it the origin of the universe if absolute nothing is a state that the laws of physics cannot accommodate. The universe as we know it spans 93 billion light-years in diameter, the observable portion alone. 1 light-year is roughly 9.5 trillion kilometers. The nearest star to our sun, Proxima Centauri, is 4.2 light-years away. a distance that a commercial aircraft flying at 900 kilometers per hour would take approximately 5 million years to cover. Now multiply that distance by 9.5 trillion. Now multiply that by 93 billion. That is the observable universe. And it all traces back to a region smaller than an atomic nucleus, roughly 13.8 billion years ago. Where did that region come from? To answer that question, cosmologists have had to grapple with something more radical than any science fiction writer has ever imagined: the possibility that the concept of before may not apply. That time, just like space and matter and energy, is not a pre-existing stage on which the universe performs. It is part of the performance itself. Stephen Hawking, working alongside physicist James Hartle in the 1980s, proposed what is known as the no-boundary proposal, a mathematical framework suggesting that asking what came before the Big Bang is like asking what lies north of the North Pole. There is no north of north. The question assumes a geometry that does not exist. In this model, time near the Big Bang behaves more like a spatial dimension than the linear, directional flow we experience in everyday life. The beginning is not a point on a timeline. It is a closed surface, a geometry with no edge, no boundary, no moment before the first moment. That is one answer. It is elegant, it is mathematically coherent, and it is not the only one. Because other physicists, armed with different equations, different assumptions, different interpretations of the quantum nature of space-time, arrive at radically different conclusions. Some argue that the Big Bang was not a beginning at all, but a transition. A moment in a much longer cosmic history, where a previous universe, governed by different physics, filled with different structures, collapsed, bounced, and gave birth to ours. The evidence for some of these models is not merely theoretical, it is written in the oldest light in the universe. The cosmic microwave background, the afterglow of the Big Bang, a faint wash of microwave radiation permeating all of space, emitted roughly 380,000 years after the beginning, carries information about the earliest moments of cosmic history in the patterns of its temperature fluctuations. Satellites like WMAP and Planck have mapped these fluctuations to extraordinary precision. And embedded in those maps, in the statistical patterns of density variations across the sky, are signals that some cosmologists argue cannot be explained by the standard Big Bang model alone. Signals that may carry the fingerprints of what came before. In 2003, the WMAP team published data revealing what physicists call super-horizon fluctuations, density variations in the cosmic microwave background that exist on scales larger than the distance light could have traveled since the Big Bang. These fluctuations should not exist if the universe had a straightforward, singular beginning. Their existence points with overwhelming statistical significance to a period of extreme exponential expansion immediately preceding the hot Big Bang. Cosmic inflation, a phase in which the universe doubled in size in every dimension with each tiny fraction of a second that passed, stretching quantum fluctuations from subatomic scales to cosmological ones. But inflation, too, raises a question. What drove it? What was the state of the universe before inflation began? Was inflation itself eternal, stretching backward through time without a beginning? Or did it emerge from something else, something stranger, something that our physics has not yet learned to describe? The deeper you push the question, the deeper the question becomes. This is the nature of the problem. Not that science has failed, but that science has succeeded well enough to show us exactly where the map runs out. And what lies beyond the edge is not blankness, but a territory of competing theories, each internally consistent, each pointing in a different direction, each demanding a new and more complete understanding of space, time, and the nature of existence itself. The universe had a beginning. That much is established. 13.8 billion years of expansion, cooling, structure formation, and cosmic evolution all trace back to a hot, dense, extraordinarily energetic state. But whether that state was truly the first, whether anything preceded it, whether preceded even makes sense, remains one of the most profound open questions in all of science. And the answer, when it comes, will not just tell us where the universe came from. It will tell us what reality is made of at its most fundamental level, including whether the word nothing has ever meant anything at all. The physics of the Big Bang itself, the precise sequence of events in the first fractions of a second, the forces that governed them, and the extraordinary fine-tuning that produced a universe capable of stars, planets, and life, contains a hidden structure so precise, so improbably calibrated, that it has forced physicists to ask a question even more unsettling than, what came before? Why does the universe look exactly the way it needs to look for us to exist inside it? The universe does not owe us a before. That is the first thing a physicist will tell you when you press them on the question. Not dismissively, carefully. Because the word before carries an assumption so deeply embedded in human cognition that most people never notice it until it's pointed out. The assumption that time is a container, that it exists independently of everything inside it. That even if the universe had never formed, time would still be ticking somewhere, counting down to the moment when matter and energy decided to show up. That assumption is wrong. Time is not a stage on which the universe performs. It is a property of the universe itself, as physical as real, and as contingent as mass or charge. It curves in the presence of gravity. It slows near massive objects. Two atomic clocks, synchronized to within a fraction of a nanosecond and then separated, one kept at sea level, one raised to an altitude of 33 centimeters above it, will diverge measurably after just a few hours. 33 centimeters, the height of a hardback book, and gravity's grip on time is already measurable at that scale. This is not philosophy. This was measured at the National Institute of Standards and Technology in Boulder, Colorado in 2010, using optical atomic clocks accurate to within 1 second over 300 million years. The result confirmed, with laboratory precision, what Albert Einstein predicted in 1915. Gravity does not merely bend the path of light or slow the orbit of planets. It bends time itself. If gravity bends time and the Big Bang was the moment of maximum gravitational intensity, a singularity, a point of infinite density where the curvature of space-time became infinite, then asking what existed before that moment is asking what lies outside a dimension that only came into existence at that moment. The question is not unanswerable because we lack the data. It is structurally problematic. It may be the equivalent of asking what is south of the South Pole. Stephen Hawking spent decades trying to formalize exactly why. Working with cosmologist James Hartley at the University of California, Santa Barbara in the early 1980s, Hawking developed what became known as the no-boundary proposal, a framework for calculating the quantum state of the universe at its origin without requiring an initial condition imposed from outside. The core idea draws from Richard Feynman's path integral formulation of quantum mechanics, in which the probability of a system evolving from one state to another is computed not by tracing a single definitive path, but by summing the contributions of every possible path simultaneously, weighted by their probability amplitudes. Applied to cosmology, this means asking, what is the probability amplitude for the universe to have emerged in the state we observe it today, summed over all possible geometries of space-time that could have led to this configuration? The Hartley-Hawking answer introduces a mathematical sleight of hand that is, on reflection, genuinely extraordinary. To make the path integral tractable, to make the equations solvable, they rotate time into what mathematicians call imaginary time, a mathematical operation in which the time dimension behaves, for the purposes of calculation, like a spatial dimension. The result is a universe with no initial boundary, no edge, no first moment before which something else must be explained. Near the Big Bang, in this formalism, time gradually becomes indistinguishable from space. Not instantly, but smoothly, the way the surface of a sphere curves without ever reaching an edge. You can walk in any direction on a sphere indefinitely. You never fall off. You never encounter a wall. The no-boundary proposal says the geometry of the early universe has this same property: closed, smooth, finite, and edgeless. The technical controversy this proposal generated has never fully resolved. In 2018, physicists Job Feldbrugge, Jean-Luc Lenners, and Neil Turok published a detailed analysis arguing that the Lorentzian version of the Hartley-Hawking path integral, the version that describes the actual real-time evolution of the universe, does not converge to a stable predictive result. Their calculations suggested the no-boundary wave function, rather than predicting a smooth and uniform early universe, actually predicts a universe dominated by violent, unstable quantum fluctuations. Hawking's collaborators disputed the analysis. The debate remains active in the theoretical physics literature. This is what real science looks like at its frontier, not consensus, not settled answers. Competing mathematical frameworks, each internally rigorous, each making different predictions, each waiting for observational data precise enough to adjudicate between them. And the observational data, when it arrives, tends to be humbling. The cosmic microwave background, the faint thermal afterglow of the Big Bang, discovered accidentally in 1965 by Arno Penzias and Robert Wilson at Bell Telephone Laboratories in New Jersey, who initially thought the persistent noise in their microwave antenna was caused by pigeon droppings, is the oldest electromagnetic signal in the observable universe. It was emitted roughly 380,000 years after the Big Bang, when the universe cooled enough for electrons to combine with protons and form neutral hydrogen atoms for the first time. Before that moment, the cosmos was an opaque plasma, too hot, too ionized for light to travel freely. The moment neutral hydrogen formed, the universe became transparent. Photons that had been trapped, scattered endlessly through the plasma, suddenly streamed outward in all directions. Those photons are still traveling. They are arriving at Earth right now, from every direction in the sky, carrying an imprint of the universe as it existed 380,000 years after its birth. Their average temperature today is 2.725 Kelvin, 2.725 degrees above absolute zero, and they are uniform to roughly 1 part in 100,000 across the entire sky. That uniformity is itself a major problem that the standard Big Bang model without modification cannot explain. The problem is called the horizon problem. Two regions of the sky on opposite sides of the observable universe, separated by roughly 93 billion light-years, have nearly identical temperatures. They differ by less than 100,000th of a degree. Under normal expansion, those two regions would never have been in causal contact. Light, traveling at 300,000 kilometers per second, would not have had enough time since the Big Bang to carry information between them. They should not know about each other. They should not have had the opportunity to equilibrate. Yet they are, for all observational purposes, at the same temperature. The leading solution to the horizon problem is cosmic inflation, a period of exponential expansion in the first tiny fraction of a second after the Big Bang, or, in some models, triggering the Big Bang itself, during which the universe expanded by a factor of at least 10 to the power of 26 in an interval of time shorter than 10 to the negative 32 seconds. Before inflation, regions that are today causally disconnected were in intimate thermal contact. Inflation stretched them apart, beyond each other's horizons, while imprinting their shared temperature across the entire observable sky. To provide a sense of what that expansion rate means, if a single hydrogen atom, 1/10 of a nanometer across, underwent the same proportional expansion as the universe did during inflation, it would end the process larger than the observable universe. Not the size of the Earth, not the size of the solar system, not the size of the galaxy. Larger than everything we can see in any direction, to the edge of the observable cosmos. That is the scale of what inflation describes, compressed into an interval of time so brief that no unit in everyday language can meaningfully represent it. Inflation was first proposed in 1980 by physicist Alan Guth, then a postdoctoral researcher at SLAC National Accelerator Laboratory in California. Guth was not trying to explain the origin of the universe. He was trying to explain why the universe contains no magnetic monopoles, hypothetical particles predicted by grand unified theories that should have been produced in enormous quantities during the hot early universe but have never been detected. His inflationary model solved the monopole problem, the horizon problem, and the flatness problem simultaneously. The flatness problem is the observational fact that the geometry of the universe is spatially flat, neither positively curved like a sphere nor negatively curved like a saddle, to a precision of better than 1%, a condition that requires the initial energy density of the universe to have been fine-tuned to within 1 part in 10 to the power of 60. Inflation does not eliminate the need for fine-tuning. It relocates it. Instead of asking why the initial conditions of the Big Bang were so precisely calibrated, you now ask, what drove inflation? What was the field? The inflaton, in the language of theoretical physics, whose potential energy density dominated the early universe and drove exponential expansion. What determined its properties? What ended inflation, and how did the violent process called reheating, in which the inflaton's energy was converted into the hot plasma of the standard Big Bang, proceed? With enough precision to produce a universe this ordered? These are not rhetorical questions. They are active research programs. And they all converge on a single boundary, a moment before which our equations carry no information, before which the physical concepts we use to describe reality may not apply. That boundary has a name. Physicists call it the Planck time, 10 to the negative 43 seconds after the Big Bang. At that moment, the energy density of the universe exceeded the Planck energy, approximately 1.96 times 10 to the power of 9 joules, concentrated into a volume with a radius of 1.6 times 10 to the negative 35 meters. At that scale, quantum gravitational effects dominate, and neither general relativity nor quantum field theory individually can describe what happens. What lies beyond that boundary, what the universe was doing, if it was doing anything, in the regime where both of our most powerful physical theories break down simultaneously, is the deepest open question in all of science. The answer may require a theory that has not yet been written. And the first clues to what that theory might look like have already been found, not in a laboratory, but pressed into the oldest light in the universe, in patterns so subtle they were nearly dismissed as instrumental noise. The universe has a temperature, not metaphorically, physically. Right now, the space between galaxies, the vast, near-perfect vacuum of intergalactic space, sits at 2.725 Kelvin, 2.725 degrees above absolute zero. That number is not an average or an estimate derived from a model. It is a direct measurement of the thermal radiation filling all of space in every direction, the cooled remnant of an epoch when the entire cosmos was a plasma hotter than the core of any star that exists today. Every cubic centimeter of space, including the air between your fingers as you read this, contains roughly 411 photons from the cosmic microwave background. They pass through you continuously, in every direction, at 300,000 kilometers per second, carrying the thermal memory of an event 13.8 billion years in the past. That temperature, 2.725 Kelvin, is a direct consequence of expansion. When a gas expands, it cools. The universe is the largest gas that has ever existed, and it has been expanding and cooling since the first instant of the hot Big Bang. Run the expansion backward. Compress the universe. The temperature rises. Compress it further, and the temperature climbs past the point where molecules can hold together, past the point where atoms can hold together, past the point where atomic nuclei can survive intact, into a regime where the fundamental forces of nature themselves begin to unify and lose their individual identities. This is the domain of particle physics. And the history of particle physics is, in its deepest structure, a history of the early universe. The four forces that govern all physical interactions, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, do not behave identically across all energy scales. At the energies accessible in everyday life, they are distinct, operating at different ranges with different strengths through different carrier particles. But theoretical physics, confirmed by decades of experimental work at particle accelerators, shows that at sufficiently high energies, some of these forces merge. Electromagnetism and the weak nuclear force unify into a single electroweak force at energies above approximately 100 giga-electron volts. An energy scale routinely achieved at the Large Hadron Collider at CERN, where the W and Z bosons that carry the weak force were first directly detected in 1983. 100 giga-electron volts is an energy scale corresponding to a temperature of roughly 10 to the power of 15 Kelvin. The universe passed through that temperature approximately 10 to the negative 12 seconds after the Big Bang. In the first trillionth of a second of cosmic history, electromagnetism and the weak force were a single unified interaction. The universe was so hot, so energetically extreme that the distinction between them had not yet emerged. Go further back. Pushed to higher energies, 10 to the power of 25 giga-electron volts. And grand unified theories predict that the strong nuclear force merges with the electroweak force into a single grand unified interaction. The temperature corresponding to that energy is roughly 10 to the power of 28 Kelvin. The universe reached that temperature at approximately 10 to the negative 36 seconds after the Big Bang. In that window, a window of time so brief that no human analogy can compress it into an intelligible comparison, the strong force and the electroweak force were indistinguishable. The quarks that make up every proton and neutron in your body, the electrons orbiting every atom, and the neutrinos passing through Earth at billions per square centimeter per second were all governed by a single unified force. And at the very edge of our theoretical reach, 10 to the power of 19 giga-electron volts, the Planck energy, gravity itself is expected to unify with the other three forces into a single master interaction. That is the temperature of the Planck epoch, 10 to the power of 32 Kelvin. The universe was at that temperature for the first 10 to the negative 43 seconds of its existence, the Planck time. And during that interval, quantum gravitational effects dominated everything. Space-time itself was not smooth. It was foaming, fluctuating, a seething quantum geometry in which the very concepts of position, distance, and duration lost their classical meaning. This is where the standard model of particle physics ends. And it ends not with a clean boundary, but with an admission. We do not have the physics to describe what happened at the Planck scale. Every equation we possess, when pushed to that regime, either diverges to infinity, produces nonsensical outputs, or requires inputs we cannot theoretically derive or experimentally measure. The singularity at the heart of the Big Bang is not just an extreme physical state. It is a breakdown of description itself. Understanding what that breakdown means requires understanding what quantum mechanics says about the nature of fields. Every particle in the universe is, in the framework of quantum field theory, an excitation of an underlying field that permeates all of space. The photon is an excitation of the electromagnetic field. The electron is an excitation of the electron field. The Higgs boson, detected at the Large Hadron Collider in 2012 after a 48-year search following its theoretical prediction by Peter Higgs and others in 1964, is an excitation of the Higgs field, a scalar field that permeates all of space and interacts with other particles to give them mass. The Higgs field, in its current state, sits in what physicists call its ground state, or vacuum expectation value, a non-zero value of approximately 246 giga-electron volts that it acquired when the universe cooled past a critical temperature in the first 10 to the negative 12 seconds after the Big Bang. Before that moment, the Higgs field had a different vacuum expectation value. Particles that today carry mass, the W and Z bosons, quarks, electrons, were massless. The electroweak symmetry was unbroken. The transition from that state to the current state is called electroweak symmetry breaking, and it represents one of the most consequential phase transitions in the history of the universe. A moment when the structure of reality itself reorganized. Phase transitions are familiar from everyday experience. Water transitions from liquid to solid at 0 degrees Celsius, releasing latent heat and reorganizing its molecular structure into crystalline ice. The transition is sharp, decisive, and irreversible under normal conditions. The early universe underwent a sequence of analogous transitions, cosmological phase transitions, as it cooled, each one reorganizing the fundamental fields and forces that govern matter. Each transition released energy. Each one left a permanent imprint on the structure of the cosmos. The QCD phase transition. The moment when the strong nuclear force, as the universe cooled below approximately 150 mega-electron volts at roughly 10 to the negative 5 seconds after the Big Bang, caused free quarks and gluons to bind together into hadrons, the composite particles that include protons and neutrons, is the transition that created the matter from which all visible structure in the universe is built. Before that moment, the universe was a quark-gluon plasma, a state of matter in which quarks moved freely without being confined inside hadrons. After it, Every quark in the observable universe was locked inside a proton or a neutron or another hadron permanently by a force so strong that separating two quarks requires more energy than it takes to create an entirely new quark-antiquark pair from the vacuum, which is what actually happens when you try. That is what the strong nuclear force means in practice. It is not merely a force that holds nuclei together. It is a confinement mechanism. It is a physical law that ensures quarks are never observed in isolation in the current universe, regardless of how much energy you apply to separate them. The energy you invest in the separation does not free the quark. It materializes as new particles. This confinement, and the QCD phase transition that established it, is directly responsible for the mass of the visible universe. The Higgs mechanism accounts for only a small fraction of the mass of a proton or neutron. The majority of a proton's mass, roughly 93%, comes not from the masses of its constituent quarks, but from the energy of the gluon field and the kinetic energy of the quarks themselves, perpetually confined and perpetually interacting at nearly the speed of light inside a region 10 to the negative 15 meters across. The proton's mass is in large part the mass of motion and interaction, energy converted into mass by Einstein's equivalence, E equals mc squared, playing out inside every atomic nucleus in your body. Go back further still. Push past the QCD transition, past electroweak symmetry breaking, past the grand unification scale, and you arrive at the epoch of inflation, the period of exponential expansion that preceded or triggered the hot Big Bang. The leading class of inflationary models posits a scalar field, the inflaton, whose potential energy density drove the expansion. The inflaton sat, initially, in a false vacuum, a metastable high-energy state, not the true minimum of its potential energy landscape. Inflation proceeded as long as the inflaton remained in this false vacuum, and it ended when the inflaton rolled down its potential toward the true vacuum, releasing its energy through a process called reheating, the violent conversion of the inflaton field's energy into the hot plasma of quarks, gluons, photons, and other particles that constitutes the standard Big Bang. Reheating is not well understood. The precise mechanism by which inflaton energy converts to standard model particles depends on the specific inflationary model and the couplings between the inflaton field and known particle fields, parameters that are not predicted from first principles and cannot yet be directly measured. What is known is that reheating must have been efficient enough to produce a universe at a temperature above the electroweak scale, and that it must have proceeded with sufficient homogeneity to explain the near-perfect uniformity of the cosmic microwave background. The inflaton field itself, if inflation occurred, left a specific fingerprint in the cosmic microwave background, a background of primordial gravitational waves generated by quantum fluctuations of the metric during inflation that would imprint a characteristic swirling polarization pattern on the microwave background known as B-mode polarization. Detection of that signal would constitute direct observational evidence of inflation. The BICEP-2 experiment announced a detection of B-mode polarization in 2014, generating enormous excitement in the cosmological community, before subsequent analysis by the Planck satellite team demonstrated that the signal was consistent with polarized dust emission from within the Milky Way, not primordial gravitational waves. The search continues. Several experiments, including BICEP Array, the Simons Observatory, and the upcoming CMB-S4 project, are designed with the sensitivity to detect or definitively rule out the primordial gravitational wave signal at the level predicted by the simplest inflationary models. If detected, the amplitude of that signal, quantified by what physicists call the tensor-to-scalar ratio, would directly measure the energy scale at which inflation occurred, fixing, with observational precision, the moment in cosmic history when the inflaton field dominated the universe. That moment is approximately 10 to the negative 36 seconds after the Big Bang, a time so close to the origin that the interval between it and the Planck time, 10 to the negative 43 seconds, contains, in some sense, more unknowns than all of subsequent cosmic history combined. Because in that 7-decade span of powers of 10, from 10 to the negative 43 to 10 to the negative 36 seconds, lies the territory where quantum gravity operates, where the distinction between space and time may have been meaningless, and where the conditions that made our universe this specific universe, rather than any other, were established. What set those conditions? What determined the value of the inflaton field's potential? What selected the laws of physics themselves, the masses of particles, the strengths of forces, the number of spatial dimensions, that inflation then imprinted at enormous scale across the fabric of everything that followed? The data already gathered suggests those questions have answers. Whether those answers are accessible to observation, whether the universe has left us enough clues in the light it has shed, is a question that a single extraordinary discovery is about to make urgently, uncomfortably real. In 1948, two physicists published a prediction so precise it should have been famous long before it was confirmed. Ralph Alpher and Robert Herman, working at the Johns Hopkins Applied Physics Laboratory in Maryland under the mentorship of George Gamow, calculated that if the universe had begun in an extremely hot, dense state and expanded over billions of years, the thermal radiation from that early epoch should still exist, cooled by the expansion of space to a temperature of approximately 5 Kelvin, 5 degrees above absolute zero, filling all of space, arriving equally from every direction, carrying no information about any particular source because it would have originated everywhere simultaneously. They published the number. They explained its physical basis. They moved on. Nobody listened. The dominant cosmological framework of the late 1940s and early 1950s was not the Big Bang. The competing model, steady-state cosmology, developed by Fred Hoyle, Herman Bondi, and Thomas Gold in 1948, the same year Alpher and Herman published their prediction, held that the universe had no beginning and no end. In the steady-state model, the universe expands, but matter is continuously created from nothing at a rate precisely sufficient to maintain a constant average density. The universe looks the same at all times and from all locations. There is no hot early epoch. There is no thermal afterglow. The prediction of Alpher and Herman in this intellectual climate was not refuted. It was simply not pursued. This is how scientific revolutions actually work. Not through immediate recognition and decisive confirmation, but through decades of parallel effort, overlooked data, and institutional inertia that occasionally, without warning, collapses. The collapse came from Bell Telephone Laboratories in Holmdel, New Jersey, not from a university cosmology department, not from a dedicated space observatory, from an industrial research facility whose primary interest in microwave radio astronomy was the practical problem of satellite communications. Arno Penzias and Robert Wilson were radio engineers. Their instrument was a 20-foot horn-shaped antenna originally built to communicate with the Echo balloon satellites. In 1964, they were attempting to use it for radio astronomy, specifically to make precise measurements of radio emission from the Milky Way. To do that, they needed to account for and eliminate every possible source of noise in the system. They identified contributions from the electronics themselves, from radio frequency interference, from the atmosphere. They accounted for all of them, and there remained, stubbornly, a residual noise signal with an equivalent antenna temperature of 3.5 Kelvin that they could not eliminate. It came from every direction equally. It did not vary with the time of day or the season of the year. It did not correlate with any known radio source. Penzias and Wilson inspected the antenna physically, found that pigeons had been nesting in the horn, and had coated the interior with what they diplomatically described in their published paper as white dielectric material, cleaned it thoroughly, and measured the noise again. It was still there. 3.5 Kelvin, arriving uniformly from the entire sky, with no identifiable source. They did not know what it was. Robert Dick, at Princeton University, 37 miles away, did know. Or rather, he had independently re-derived the prediction of Alpher and Herman and was in the process of building an instrument to search for exactly this signal when Penzias called him. The account of that phone call has since entered the history of science. Dickey hung up, turned to his colleagues, and said, "Boys, we've been scooped." The two papers were published side by side in the Astrophysical Journal in July 1965. Penzias and Wilson reported the anomalous noise. Dickey, Peebles, Roll, and Wilkinson provided the cosmological interpretation. The universe had a thermal history. The Big Bang was not a hypothesis. It was a measurement. In 1978, Penzias and Wilson received the Nobel Prize in Physics for the discovery. But the discovery of the cosmic microwave background's existence was only the beginning. What it contained, encoded in the faint temperature variations across the sky at the level of 1 part in 100,000, was far more consequential than the signal itself. The COBE satellite, the Cosmic Background Explorer, launched by NASA in November 1989, carried 3 instruments designed to measure the microwave background with a precision no ground-based telescope could achieve. The differential microwave radiometer, designed specifically to map temperature fluctuations across the sky, operated at 3 frequencies simultaneously, scanning the entire sky every 6 months. After 2 years of data collection and painstaking analysis to remove foreground contamination from the Milky Way, the COBE team, led by George Smoot at Lawrence Berkeley Laboratory and John Mather at NASA Goddard Space Flight Center, announced their result on April 23, 1992. They had detected the primordial temperature fluctuations, the anisotropies, at the level of roughly 30 microkelvin, 30 millionths of a degree. Variations in the temperature of the cosmic microwave background that represent density fluctuations in the early universe, regions marginally denser or slightly more rarefied than average, present 380,000 years after the Big Bang. These fluctuations, amplified over 13.8 billion years by gravity, became every galaxy cluster, every filament, every void in the observable universe. The large-scale structure of the cosmos, traced today by surveys of hundreds of millions of galaxies stretching billions of light-years in every direction, grew from seeds of density contrast smaller than 1 part in 100,000 in the primordial plasma. Smoot described the COBE maps as seeing the face of God. The characterization was widely reported and widely criticized as imprecise. But the scientific substance beneath the metaphor was extraordinary. The universe's entire visible architecture, every gravitationally bound structure in the observable cosmos, originated in quantum fluctuations, microscopic probabilistic variations in energy density at scales far smaller than a proton. That inflation stretched to cosmological dimensions, and the subsequent 13 billion years of gravitational dynamics amplified into the structures we observe. The Nobel Prize in Physics for 2006 went to Mather and Smoot for this discovery. The WMAP satellite, the Wilkinson Microwave Anisotropy Probe, launched in June 2001, extended COBE's maps by more than an order of magnitude in angular resolution. Where COBE could resolve features larger than roughly 7 degrees on the sky, WMAP resolved features down to a fraction of a degree. The resulting maps revealed the acoustic oscillation peaks in the power spectrum of CMB temperature fluctuations, specific angular scales at which the fluctuation amplitude is enhanced, with enough precision to constrain the geometry, composition, and expansion history of the universe simultaneously. The acoustic peaks arise from a physical process as elegant as any in cosmology. In the hot plasma of the early universe, overdense regions, those seed fluctuations from inflation, began to collapse under gravity. As they collapsed, radiation pressure from the photons trapped in the plasma pushed back, halting the collapse and driving an outward expansion. That expansion then overshot, creating an underdense region, which then collapsed again. The plasma oscillated, contracted, and expanded, like a sound wave propagating through the primordial fluid. When the universe became transparent at 380,000 years, these oscillations froze in place, imprinted on the photons that then streamed freely across space. The angular scale of the first acoustic peak, the scale at which the oscillation had completed exactly 1 compression, corresponds to the distance sound could travel in the primordial plasma before it froze. That distance is called the sound horizon, approximately 450 light-years at the time of recombination, stretched by subsequent expansion to approximately 450 megaparsecs in the present universe. The Planck satellite, launched by the European Space Agency in May 2009, equipped with detectors cooled to 1/10 of a Kelvin using a 3-stage cryogenic system, produced the highest precision maps of the cosmic microwave background ever made. Its 2013 and 2015 data releases constrained the age of the universe to 13.813 billion years with an uncertainty of less than 1%, measured the Hubble constant, the rate of cosmic expansion, at 67.3 kilometers per second per megaparsec, determined that the universe is composed of approximately 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy, and confirmed that the spatial geometry of the universe is flat to a precision of better than 0.5%. Each of those numbers carries the fingerprint of the early universe. The proportion of dark matter controls the height of the acoustic peaks. The proportion of dark energy controls the expansion history. The flatness of geometry confirms inflation's prediction. Every parameter derived from the Planck data is a message from the first 380,000 years of cosmic history, encoded in the temperature of photons that have been traveling for 13.8 billion years. And yet, embedded in the Planck data, there are anomalies. Statistical features of the CMB temperature map that the standard cosmological model, lambda CDM, the model incorporating dark matter and dark energy, cannot fully account for. A suppression of power at the largest angular scales. An unexpected alignment between the quadrupole and octupole moments of the temperature map, the largest scale features of the sky, with each other and with the geometry of the solar system, in a configuration so improbable that the Planck team named it the axis of evil. The probability of this alignment occurring by chance in a universe described by lambda CDM is less than 1%. These anomalies may be statistical flukes. The universe is a single realization of its own statistics, and rare configurations occur. But they may also be the first observational indication of physics operating at scales larger than the observable universe. Physics that was active before inflation ended, physics that imprinted structure on scales that inflation then expanded beyond our current cosmic horizon. They may, in other words, be the first direct evidence that our observable universe is not all there is. That what we can see, the sphere of space from which light has had time to reach us in 13.8 billion years, roughly 46 billion light years in every direction, is an infinitesimal patch of a vastly larger structure, shaped by processes that occurred before the hot Big Bang, in a regime our instruments have only just begun to interrogate. The anomalies in the oldest light in the universe are small, subtle, they would be easy to dismiss. Except that a completely independent line of evidence, from a completely different instrument, measuring a completely different physical phenomenon, is pointing in precisely the same direction. On September 14th, 2015, at 5:51 in the morning Eastern Daylight Time, a ripple in the fabric of space-time passed through the Earth. It had been traveling for 1.3 billion years. The signal lasted less than 0.2 of a second. During that interval, the two arms of the LIGO detector in Livingston, Louisiana, each a vacuum tube 4 kilometers long, through which laser beams bounced between mirrors suspended from glass fibers thinner than a human hair, in a system isolated from ground vibration by a multi-stage pendulum apparatus weighing several tons, changed in relative length by a distance of 4/1000ths of a femtometer. A femtometer is 10 to the negative 15 meters, the diameter of a proton. 4/1000ths of that, a displacement equivalent to 1/10,000th of the diameter of a single proton, detected across a baseline of 4 kilometers, by a laser interferometer whose mirrors are among the most precisely positioned objects ever manufactured by human beings. The signal matched, with extraordinary fidelity, the theoretical prediction for the gravitational waveform produced by two black holes, one of 29 solar masses, one of 36 solar masses, spiraling toward each other at a significant fraction of the speed of light, merging into a single black hole of 62 solar masses, and radiating the remaining 3 solar masses as pure gravitational wave energy in the final fraction of a second of the inspiral. 3 solar masses, 3 times the mass of the Sun, each containing 2 times 10 to the power of 30 kilograms, converted entirely to gravitational radiation in under a second. The peak power output during the merger was approximately 3.6 times 10 to the power of 49 watts. For that fraction of a second, this single event radiated more power than the combined electromagnetic output of every star in the observable universe. This was the first direct detection of gravitational waves. It confirmed a prediction Einstein had made in 1916. exactly 99 years before the signal arrived, when he derived from the field equations of general relativity that accelerating masses must radiate energy in the form of ripples in the space-time metric, oscillations in the geometry of space itself, propagating outward at the speed of light. Einstein himself later doubted whether gravitational waves were physically real or merely mathematical artifacts of his coordinate system. They are real. The LIGO-Virgo collaboration has since cataloged over 90 confirmed gravitational wave events, from black hole mergers, neutron-star mergers, and mixed compact object systems, each one a direct measurement of curved space-time dynamics in the most extreme physical environments the universe produces. Gravitational waves do not interact with matter the way electromagnetic radiation does. A photon can be absorbed, scattered, reflected. A gravitational wave passes through everything, through planets, through stars, through the entire Earth, with essentially zero attenuation. This property, which makes them extraordinarily difficult to detect, also makes them extraordinarily valuable as cosmological probes. They carry information from environments that are completely opaque to light, from inside neutron stars, from within the event horizons of merging black holes, from epochs of cosmic history that preceded the emission of the cosmic microwave background. The universe was opaque to electromagnetic radiation for the first 380,000 years of its existence. The primordial plasma scattered photons so efficiently that light could not travel freely in any direction. The cosmic microwave background represents the oldest electromagnetic signal we can ever receive, a hard limit imposed by the physics of recombination on our ability to see the universe's earliest history using light. Gravitational waves have no such limit. Primordial gravitational waves, the background of tensor perturbations generated by quantum fluctuations of the space-time metric during inflation, would have propagated freely through the primordial plasma, through recombination, through all 13.8 billion years of subsequent cosmic history, and would be arriving at Earth today as a stochastic gravitational wave background, a faint omnidirectional hiss of space-time oscillations carrying information from the inflationary epoch itself. Their detection would constitute a direct observational window into the first 10 to the negative 32 seconds of cosmic history, the epoch before the hot Big Bang, the era the cosmic microwave background cannot reach. In 2023, 4 major pulsar timing array collaborations, the North American Nanohertz Observatory for Gravitational Waves, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Chinese Pulsar Timing Array, simultaneously announced evidence for a stochastic gravitational wave background at nanohertz frequencies. Pulsar timing arrays use millisecond pulsars, rapidly rotating neutron stars that emit radio pulses with the regularity of atomic clocks, as the arms of a galaxy-scale gravitational wave detector. A gravitational wave passing between Earth and a pulsar stretches or compresses the space between them, arriving at a period slightly different from the prediction of the pulsar's known timing model. By monitoring an array of pulsars distributed across the sky and correlating the timing residuals between them, the signal of a background of gravitational waves can be extracted. The correlation signature they searched for and found at a statistical significance of 3 to 4 sigma across all 4 collaborations is called the Hellings-Downs curve, a specific angular correlation between timing residuals and pulsar pairs as a function of the angular separation between them on the sky. The Hellings-Downs curve is the unique prediction of a gravitational wave background with the statistical properties expected from general relativity. Its detection across 4 independent datasets using different pulsars, different telescopes, different analysis pipelines in different hemispheres of the Earth is among the most significant results in observational cosmology in the past decade. The amplitude and spectral shape of the detected background are consistent with a population of supermassive black hole binaries, pairs of black holes each containing hundreds of millions or billions of solar masses, orbiting each other at the centers of merging galaxies across the observable universe, radiating gravitational waves across geological timescales. That astrophysical source is the leading explanation, but the measured signal may also contain contributions from other sources. Cosmic strings, hypothetical one-dimensional topological defects in the structure of space-time, predicted by some grand unified theories to have formed during phase transitions in the early universe, would produce a gravitational wave background with a spectral shape distinguishable from the supermassive black hole binary signal with sufficient data. A first-order phase transition in the early universe, a transition that proceeded through bubble nucleation rather than smoothly releasing energy into gravitational waves as bubble walls collided, would produce a background with a characteristic spectral peak frequency determined by the temperature of the universe at the time of the transition. Most consequentially, a background of primordial gravitational waves from inflation would have a spectral index, the dependence of its amplitude on frequency, that is nearly scale invariant, a direct analog of the near-scale invariant spectrum of density perturbations that produce the cosmic microwave background anisotropies. Distinguishing between these sources requires better data, more pulsars, longer observation baselines, higher sensitivity. The Square Kilometre Array, a radio telescope array currently under construction in South Africa and Australia, with a total collecting area of 1 square kilometre, representing the largest scientific instrument ever built, will monitor thousands of millisecond pulsars simultaneously with a sensitivity orders of magnitude beyond current pulsar timing arrays. The James Webb Space Telescope, operational since 2022, is contributing from a different direction. Its near-infrared and mid-infrared instruments are imaging galaxies at redshifts above 10, galaxies that existed when the universe was less than 500 million years old, with a resolution and sensitivity that Hubble could not achieve. In its first year of science operations, Webb discovered fully formed massive galaxies at redshifts between 12 and 17 that should not exist, according to standard models of galaxy formation, in such abundance at such early epochs. Galaxies containing hundreds of billions of solar masses of stars, apparently assembled within the first few 100 million years of cosmic history, in a universe that standard cosmological models predict should have produced only small, irregular proto-galaxies at those epochs. The discrepancy may be resolved by refinements in galaxy formation models, by better accounting for the efficiency of star formation in the early universe, or by reconsidering how the ultraviolet light from young stars is reprocessed into the infrared emission Webb detects. But the scale of the anomaly, the sheer number of unexpectedly massive early galaxies, has forced a serious re-examination of whether the standard model of cosmic structure formation, calibrated to the cosmic microwave background and the large-scale distribution of nearby galaxies, correctly extrapolates to the first few 100 million years of cosmic history. The Hubble tension sits at the center of this unease. The Hubble constant, the rate at which the universe is currently expanding, measured from the cosmic microwave background by the Planck satellite, gives 67.4 kilometers per second per megaparsec. The same constant measured from the distance ladder, from Cepheid variable stars calibrating distances to Type Ia supernovae in the local universe, gives 73.4 kilometers per second per megaparsec. The two measurements disagree by approximately 5 sigma. In physics, 5 sigma is the threshold for claiming a discovery. The two most precise measurements of the expansion rate of the universe disagree with each other at the confidence level required to announce a new particle. The Hubble tension is not a calibration error. Every systematic effect that could account for the discrepancy has been investigated, and none resolves it. It may require new physics operating in the early universe, a brief period of additional energy density before recombination, called early dark energy, that would increase the expansion rate at that epoch and shift the CMB-derived Hubble constant upward. It may require a modification of the late universe expansion history. It may reflect something about the local structure of the universe that biases distance ladder measurements. Or it may be pointing at something more fundamental, a departure from the standard cosmological model deep enough to require revising our understanding of what the universe was doing in its earliest moments. Every instrument measuring the early universe, from microwave satellites to gravitational wave detectors to infrared space telescopes, is converging on the same uncomfortable conclusion. The standard model is extraordinarily successful. It predicts the acoustic peaks of the CMB, the abundance of light elements from Big Bang nucleosynthesis, the large-scale structure of the galaxy distribution, and the accelerating expansion driven by dark energy, all with remarkable precision across an enormous range of scales and epochs. And yet, at its edges, In the largest scale anomalies of the CMB, in the Hubble tension, in the unexpectedly massive early galaxies seen by Webb, in the amplitude of the gravitational wave background, the data is accumulating pressure at the seams. Something in the standard model is incomplete. The question is whether the missing piece is a refinement of known physics, a better treatment of baryonic feedback, a more careful systematic analysis, or whether it is genuinely new. A signal from the regime before the hot Big Bang, from a physics that inflation or a predecessor state imprinted on the structure of the cosmos before the universe was a second old. The data does not yet decide, but it is closing in. And in the gap between what is known and what the instruments are beginning to measure, the deepest question in cosmology is no longer purely theoretical. It has become observational. The answer to what existed before the Big Bang may not come from a thought experiment or a mathematical framework alone. It may come from a number, a spectral index, a tensor-to-scalar ratio, a precise measurement of the Hubble constant that forces every other piece of the model to shift. The universe has been carrying that number for 13.8 billion years. We are only now building instruments sensitive enough to read it. The human brain evolved to navigate a world of middle distances. It developed intuitions calibrated to the scale of savanna and forest, to distances measured in meters, to timescales measured in seasons, to masses measured in the weight of bodies and stones. It did not evolve to process 13.8 billion years. It did not evolve to hold in mind a temperature of 10 to the power of 32 Kelvin, or a length of 10 to the negative 35 meters, or the fact that the empty space between your eyes and this page is seething with quantum fluctuations at every moment. These are not failures of imagination. They are simply the outer boundary of the cognitive range for which natural selection had any use. And yet, here we are. The same species that spent most of its existence unable to explain thunder or fire has built instruments sensitive enough to detect the stretching of space by 4/1000ths of a proton diameter across 4 kilometers of laser-lit vacuum, and used those instruments to confirm predictions made by equations written on paper in 1916. The LIGO-Virgo-Cagra collaboration completed its 4th observing run in November 2025, cataloging gravitational wave events at a rate of approximately 1 every 2 to 3 days, each one a direct measurement of curved space-time dynamics in environments so extreme that the physics operating within them approaches, and in some cases crosses, regimes our theories cannot yet fully describe. In January 2025, a gravitational wave event designated GW25014 arrived at the LIGO detectors. The clearest black hole merger signal ever recorded, clear enough for physicists to measure not just the primary frequency of the ringdown, the dying oscillation of the newly formed black hole as it settled into its final state, but 3 distinct tonal components of that ringdown simultaneously. Each tone encodes specific information about the mass and spin of the final black hole. In general relativity, all 3 tones must be consistent with the same mass-spin combination, a requirement called the no-hair theorem, which states that a black hole is completely described by just 3 numbers: its mass, its spin, and its electric charge. GW250114's tones matched, all 3. To the precision of the measurement, general relativity held. But the significance of that result lies not only in the confirmation, it lies in what a future deviation would mean. Any gravitational wave signal in which the ringdown tones do not match the no-hair prediction would constitute direct observational evidence that general relativity is incomplete, that the geometry of space-time near a black hole horizon differs from what Einstein's equations predict. That deviation, if it exists, would carry the signature of quantum gravity, the physics that must eventually replace general relativity at the Planck scale, the physics that governed the first 10 to the negative 43 seconds of cosmic history, the physics of whatever preceded the Big Bang. The Einstein telescope, a proposed 3rd-generation gravitational wave observatory to be built underground in Europe with arm lengths of 10 kilometers, and Cosmic Explorer, its American counterpart with arms 40 kilometers long, will operate at sensitivities 10 to 100 times beyond current LIGO. They will detect black hole mergers across the entire observable universe, including mergers that occurred in the first few hundred million years after the Big Bang, at redshifts above 10, in the same epoch where the James Webb Space Telescope has found its unexpected population of massive early galaxies. Each merger at that epoch is a data point on the expansion history of the early universe, an independent measurement of the Hubble constant at a cosmic distance beyond the reach of any current instrument. LISA, the Laser Interferometer Space Antenna, a gravitational wave observatory consisting of 3 spacecraft in a triangular formation with arm lengths of 2.5 million kilometers, scheduled for launch by the European Space Agency in the mid-2030s, will operate at millihertz frequencies, a range inaccessible to ground-based detectors. At those frequencies, LISA will observe supermassive black hole mergers across cosmic history, the inspiral of compact objects into supermassive black holes in galactic centers, and, if the signal is strong enough, a stochastic gravitational wave background from the early universe. Its sensitivity in the millihertz band will probe cosmological phase transitions at energy scales corresponding to the electroweak epoch, the first 10 to the negative 12 seconds of cosmic history, the moment when the Higgs field settled into its current state and the electroweak symmetry broke. And LIGHTBIRD, the light satellite for the studies of B-mode polarization and inflation from cosmic background radiation detection, a Japanese space agency mission planned for launch in the early 2030s, will measure the B-mode polarization of the cosmic microwave background with a sensitivity designed to detect the primordial gravitational wave signal from inflation at tensor-to-scalar ratios as small as 10 to the negative 3. If inflation occurred at the energy scales predicted by the simplest single-field slow-roll models, LIGHTBIRD will find its signal. If it does not find it at the predicted level, the simplest models will be ruled out, and the theoretical landscape of inflationary cosmology will narrow dramatically. Either result is decisive. Either result tells us something fundamental about the energy scale at which the universe emerged from its pre-Big Bang state. These instruments, LIGO's 5th observing run beginning in late 2026, the Square Kilometer Array accumulating pulsar timing data, Webb mapping the earliest galaxy population, LIGHTBIRD and LISA in development, are not incremental refinements of existing knowledge. They represent a qualitative shift in humanity's observational access to cosmic history. For the first time, multiple independent physical channels, electromagnetic radiation, gravitational waves, neutrinos from supernovae, and potentially the stochastic backgrounds from phase transitions can be cross-correlated to reconstruct a picture of the early universe from overlapping perspectives that no single instrument can provide alone. The convergence of these datasets in the coming decade will either confirm the standard cosmological model with unprecedented precision, resolving the Hubble tension and the CMB anomalies through better systematics, or it will break the model. Not catastrophically. Not in a way that invalidates what is already known. General relativity will remain the correct description of gravity in the regimes where it has been tested. The standard model of particle physics will remain the correct description of particle interactions at accessible energies. What will break, if the model breaks, is the extrapolation, the assumption that the physics we understand, applied to the initial conditions we infer from the CMB, correctly describes what happened before inflation, or during inflation, or in the Planck epoch before any of our current frameworks apply. That extrapolation has always been an assumption. Science has always known it was an assumption. What is changing now is the observational leverage to test it. Here is what is established, beyond reasonable scientific doubt. The universe has been expanding and cooling for 13.8 billion years. Its large-scale structure, galaxies, clusters, filaments, voids, grew from density fluctuations present at the time of the cosmic microwave background, fluctuations that are consistent with having been generated by a period of inflationary expansion. The universe is spatially flat to the limits of current measurement. It is composed predominantly of dark matter and dark energy, whose physical nature remains unknown. The cosmic microwave background carries anomalies at large angular scales that the standard model does not fully explain. The two most precise measurements of the Hubble constant disagree at 5 sigma. The James Webb Space Telescope has found galaxies more massive than the standard model predicts at redshifts above 12. The pulsar timing arrays have detected a stochastic gravitational wave background, consistent with a population of supermassive black hole binaries, with possible contributions from early universe sources not yet ruled out. Each of these facts individually is a precisely measured number. Together, they sketch the outline of a question that physics has not yet answered, but is, for the first time in history, closing in on with instruments capable of generating a decisive answer. The question is not merely cosmological. It is the question beneath all other questions in physics. Is there a complete, consistent description of nature that applies from the smallest measurable scale to the largest, from the first instant of the universe's existence to its final state, from the quantum vacuum to the geometry of space-time? Does such a description exist? And if it exists, does it describe a universe that had an absolute beginning, a first moment before which the concept of before is undefined, or a universe embedded in a larger structure, a deeper physics, an eternal substrate of which the Big Bang was one event among many? 13.8 billion years ago, in a state our equations cannot fully describe, the conditions that made this universe, this specific configuration of matter, energy, space, and time, were established. Every atom in every star in every galaxy in the observable cosmos traces its origin to that moment. The carbon in organic molecules, forged in stellar cores and scattered by supernova explosions across billions of years. The hydrogen in every ocean, created in the first 3 minutes after the Big Bang in the process of primordial nucleosynthesis, when protons and neutrons combined for the first time into deuterium, helium, and lithium at temperatures above 10 million Kelvin in a universe younger than any star that now exists. The photons arriving at every telescope, carrying information from the edges of the observable cosmos, from epochs when the universe was a fraction of its current age, from structures that no human eye will ever observe directly because the light from beyond the cosmic horizon will never reach us. All of it, every measurement, every observation, every number extracted from every instrument ever built, points back to a boundary, a limit. A moment at which the known laws of physics reach the edge of their jurisdiction. What lies beyond that boundary is not known. It may never be fully known. The cosmic horizon limits our observational reach in space. The Planck time limits our theoretical reach backward in time. Between those two limits, the observable universe and the first 10 to the negative 43 seconds, lies everything science has ever measured, every law it has ever confirmed, every structure it has ever mapped. That is an extraordinary amount of knowledge built on an extraordinarily thin slice of what may exist. The universe does not require our understanding to function. It has been doing so with perfect fidelity to its own laws for 13.8 billion years. Whether those laws had a beginning, whether they emerged from something else, whether something and nothing are even coherent categories at the scales where space and time dissolve into quantum geometry, these are questions for which the universe has left evidence scattered across the oldest light and the deepest silence. We are the only part of the universe, as far as we know, that is asking them.